So ionic bonding, like I said, is when metals lose electrons, and where do they go? They don't just disappear. Where do they go? Not noble gases, but you're on the right track. Right? It's that same side of the periodic table. If metals lose them, where do they go? The non-metals. So when the metals lose their electrons, we said they form a positive charge, they're cations. The non-metal gains the electron and becomes an anion. And we said whether they're +1, +2, -1, -2, in the end, all comes down to what their valence electrons are to begin with, right? If they have one extra one, they're going to lose it to fall back. They have 8 valence electrons. If they have 7, they're going to gain one to go forward to 8. In the end, they end up with a noble gas electron configuration. So I think we've seen this picture before. You have sodium metal, chlorine gas, you put them together, and you get sodium chloride. What's actually happening in this reaction are the electrons are being transferred from the sodium to the chlorine, and what happens is you get the sodium positive and the chlorine negative, opposites attract, and they have an ionic bond holding them together. So when you look at a chunk of an ionic compound, remember we have this repeating pattern of atoms. So here, our green ones are our chlorines, and our yellow ones are our sodiums. And so these yellow ones have positive charge, the green ones have a negative charge. So we don't just have forces of attraction going on here, because we have multiple positives and we have multiple negatives next to each other. So going on all at the same time, we have forces of attraction between the chlorines and the sodiums, and the repulsion between the sodiums and the sodiums, and the chlorines and the chlorines. And all those forces together causes the atoms to find their happy place, where all the forces completely balance, and it just sits there in our crystal lattice. If this moved over a little bit, the forces would push it right back to where it is. Ionic solids are crystalline, and they're hard and brittle. Looking at this picture, can someone try to come up with an explanation of why ionic solids are hard? Ignore the brittleness at the moment.
Because of how close they are.
They're very close together, and hard to me means you can't easily move, you can't bend it. If you bend it or you push something, these atoms are going to try to move. And what did we say happens when those atoms try to move? They get pushed right back. And so as you push, they're pushing back. And so the solids are hard. Now the trickier one is brittleness. Why do you think ionic solids are brittle? And when I say brittle, I mean they break with very clean lines. If I took a pencil and I break it in half, I'm not going to get a perfectly clean break. If I take sodium chloride and I break it, I'm going to get perfectly clean lines. Why do you think you get that from something shaped like that? Think of it. If you have sodium chloride, it's NaCl. What does that formula tell you about the ratio between sodiums and chlorines? Equal amount, 1 to 1. And so, if you were to have to break this, if you break it in a straight line, you're going to end up with 1 to 1 ratios. If you break it in a jagged line, you may not end up with a 1 to 1 ratio. So ionic compounds break in straight lines. They're brittle. Ionic compounds don't conduct electricity when they're in a solid state. And I'm going to tell you that for something to conduct electricity, there have to be charges that can move. Conduction of electricity is the movement of charges. Why do you think an ionic compound does not conduct electricity when it's in the solid form.
Because the charges don't move.
Why don't they move?
So close together.
They're so close together, and if they try to move, they get pushed right back. So even though we had plenty of negative and positive charges here, those charges can't move. So you can't conduct electricity from one side of the solid to the other. Covalent bonding is between two nonmetals. So we also still have attractive forces and repulsive forces going on in covalent bonding. Here we're looking at two atoms of the same element. What are these here?
Same charge?
In terms of the parts of an atom, what are these?
Subatomic particles.
Subatomic particles, what type? Protons. You have the positive protons in the center. So if you have two nuclei containing protons next to each other, they're going to repel each other. What are these out here?
Electrons.
Electrons. Those are negative. And so we have attractive forces between the nuclei and the electrons, but also these electrons are repelling those electrons. So again, everything moves around until it finds its happy place. And right here, all of the forces balance out, and they're stuck right there. In covalent bonding, because we have two non-metals, that means everything is coming from the right side over here. Everything on the right side wants to gain electrons. It doesn't want to lose electrons. And so if a fluorine and an oxygen come together and they say we both want to have 8 electrons, how can we do this? Because the fluorine says, I'm not giving up an electron, and the oxygen says the same thing, and so they compromise. They share an electron. When they share it, they both get the noble gas electron configuration. So this is carbon dioxide. You have carbon and oxygen, two nonmetals, so it's a covalent molecule. So they're covalent bonds. Do you think these covalent bonds are polar or nonpolar covalent?
Polar.
Why are they polar?
Because oxygen is closer to fluorine, so it has a higher
Right.
electron.
Right. So oxygen is closer to fluorine, so it's higher. Or you could even say carbon and oxygen aren't the same element, and it's not carbon-hydrogen, so by default, they have to be polar covalent. So this is the same picture we've had before, with two red oxygens and a black carbon forming that molecule. That's a carbon dioxide solid. It's dry ice. That's what dry ice looks like. And it goes from the solid straight to the gas. What's the process of going from a solid to a gas called? Sublimation. Solid to a gas. What's the other way around? Gas to a solid. Deposition. In a covalent compound, every molecule is independent of each other. This one doesn't even know that one exists. So this molecule can go anywhere it wants. This one can go anywhere it wants. In the gas, solid, and we'll call this liquid also over here. In any state, every molecule is completely independent of each other. And that's different than this. This sodium is partially paired with that chlorine, that chlorine, that chlorine, this chlorine back here, that one over there. It's just a big group of sodium and chlorine ions in a 1-to-1 ratio. You can't pick and say, this sodium goes with that chlorine. But in a covalent compound with covalent bonds, you have distinct molecules. And once you leave that molecule, you're in a different molecule, and they can be separate from each other. So, a couple weeks ago, we did the Lewis dot symbols. And I think I said, what we're going to do then is just a tiny little primer of what we're going to do with Lewis dots. And it's going to be a whole lot easier then than it was what we're going to do in the future. Well, today's the future. Okay. Now it's going to get to you. When we talk about covalent bonds, we said each one wants to get a noble gas configuration. They want to get 8 valence electrons. In a covalent compound, everything, every atom is going to have 8 electrons. The only exception is hydrogen. Hydrogen gets 2. This is called the octet rule. Octet meaning 8 electrons. So in this compound, we have a carbon in the center and 4 fluorines going around it. If you count the dots around this fluorine, we have 2, 4, 6, 8. This fluorine has 8, 8, and 8, and the carbon has 8. These 8 in the center are shared. If it's shared, they both get to count it. It's not like we're sharing this pair, so I get 1, you get 1. We both get both of them. Okay? So this carbon is happy because it has 8. These fluorines are happy because they have 8. Down here we have fluorine with hydrogen. So hydrogen only gets 2. So here, fluorine has 8, hydrogen has 2. That's the octet group. When you draw those 8 electrons, they're always going to come in pairs. Okay? In these structures that we're going to be drawing, you will never draw a single electron. If you draw a single electron, you should immediately realize you did something wrong. You always have pairs. We said hydrogen gets 2, and what we're going to do is we're going to take that rule, and we're going to draw Lewis dot symbols. Okay? We're going to draw out a covalent compound, we're going to put our dots, and we're going to make everything happy. It basically becomes a puzzle. It's not that hard once you do a few of them. It really is a puzzle. Figure out where can you put these electrons in order to make everything happy. So let's start in the simplest one possible. Hydrogen and hydrogen. Hydrogen's diatomic. We said hydrogen by itself exists as H2. So the first thing you need to do when you start to draw these is you look at each individual atom and figure out how many valence electrons it brings. So how many valence electrons does a hydrogen atom have? 1. So each hydrogen atom is going to bring 1. So how many do you have total? 2. Each hydrogen atom wants to have 2. So we put both electrons right in the center, they're both happy. So this one brings 1, this one brings 1, 2 electrons end up in the middle, and they're both happy. So these are our halogens. How many electrons, how many valence electrons does the halogen bring? 7. So it doesn't matter whether you're fluorine, chlorine, bromine, or iodine. They all bring 7 valence electrons. And so basically what you're starting with is you have fluorine, you have 2, 3, 4, 5, 6, 7. And so can you see that if you just slide these together, those 2 are going to pair up in order to make a pair, and each one now has 8. I'm going to try turning the lights on, see if they get rid of some of the glare so you can actually see the board on the video. Because we're going to be working up here pretty much all day. So if you had to tell me why do the halogens exist as diatomic molecules? Why do they? Before we just said they did and left it at that. Why do they exist as diatomic molecules? They each go to somebody who's not system.
But is it because they want that last electron?
They want the last electron. And so if they come in pairs, they can share that last electron and get the 8 that they want. How many valence electrons does an oxygen atom have? 6. How many does it need to gain in order to get an octet? 2. So, if we have O2, and we have each oxygen is going to bring 6, how many do we have total? 12. So, what we're trying to do here is arrange those 12, and so that both oxygens are happy. Can we do, are any of these correct?
No,
Why is that one not correct?
because it has to be on one side and
8 and 6. Why is this one's just flipped around? And why is that not correct? They each have 7, and there's single electrons. So without even counting, you should see that single dot and say no. So we have to do something. It can't stay like this. None of these work. So what we have to do is we have to form a double bond. We can put multiple pairs of electrons between oxygens. So basically what we do is we take this, and we take that pair, and stick it in there. So now this one has 1, 2, 3, 4, 5, 6, 7, 8. This one has 4, 5, 6, 7, 8. We end up with that. Yeah. Yeah.
so technically the 4 electrons in the middle each contain 2.
So here we have 2 pairs.
Yeah.
Yes. But both oxygens claim all 4. The nitrogen. How many valence electrons does nitrogen come with? 5. How many does it need to gain?
3.
3. Nitrogen and 2 form the triple bond. So the key here is elements that need to gain 1 electron are going to form a single bond. Elements that need 2 are going to form a double bond. Elements that need 3 will form a triple bond, if they're bonding to each other. Okay? Later on, we'll start making bigger molecules, and what it'll turn into is that things that need 1 will make 1 total bond. Oxygen, which needs 2, will make 2 total bonds, either a double bond or 2 single bonds. With nitrogen, can make a triple, it can make 3 singles, a double, or a single, and a single. Okay? But we'll do plenty of examples. So how many bonds is hydrogen going to form?
2.
Only 1 bond, but 2 electrons.
Right, it's going to end up with 2 electrons, but it starts with 1. So it needs to gain 1, so it's going to form 1 bond. What about chlorine? How many bonds is chlorine going to form? Why 1?
Because it has 7 already.
It has 7, it needs to gain 1, so it's going to make 1 bond. For every bond, it's gaining 1 electron. But oxygen
Needs 2.
it needs 2. So how many bonds? 2. Nitrogen? 3. Carbon.
4.
It needs 4, so it's going to make 4 bonds. Okay, so we made our rules. Everything has to have 8 electrons unless it's hydrogen. If it's hydrogen, it has to have 2. And then you also know how many bonds each thing likes to form. So in the end, once you write your structure, you need to make sure both of those things are satisfied. Everything has an octet, or hydrogen has 2, and every element has made the number of bonds that it likes to make. So these are some steps, okay? We're going to refer to this. We're not just going to walk you through, because if I just walk you through it now, it's not going to make any sense whatsoever. So we'll do an example. So we have CH2O. The first step is write an atomic skeleton. This means write the elements out in the shape of the molecule, but ignore the electrons for now. So generally, the first element is going to be in the center, and everything after that is going to go around it. So we have a carbon, we're going to put a carbon here, then we have two hydrogens and an oxygen. So I'm going to put hydrogen, hydrogen, oxygen. It doesn't matter whether you put the oxygen here, or the hydrogen here, and the oxygen there. It doesn't matter. You have two hydrogens and an oxygen around the carbon. Okay? Next step. How many total valence electrons do we have? So how many does carbon bring? 4. Carbon's got 4. How many does each hydrogen bring?
1.
And how many hydrogens do we have?
We have 2.
2. So we have 2 electrons from the hydrogens. And how many does the oxygen bring?
6.
6. So we have 12 total. Okay? When I do this, I add up the electrons and I write my number down. Okay? I'll draw my skeleton and I'll write my total number of electrons. Next step, place a pair between each atom. And so something has to be holding this in place. So we're going to start with single bonds. So I'm going to put single bonds between each atom. That's holding those together, that's holding those, that's holding those. 4 says any electrons that you have left, add them to the outside atoms so that they get their octet. Here we have 2 hydrogens. Their octet is actually 2. These hydrogens already have 2. Those hydrogens are happy. We cannot do anything more with those hydrogens. So we have used 6 electrons. How many do we have left? 6. So I'm going to go 1, 2, 3, 4, 5, 6. I added them to the outside atoms to make them happy. Okay? So the hydrogen has 2, hydrogen has 2, oxygen has 8. Those are all good. Is carbon happy?
No.
Why is carbon not happy?
He's only 6.
No.
It only has 6. It needs 8 or 4 pairs of electrons. It needs 4 bonds also. So what can I do here to make everybody happy?
Remove 2 from the
Acceptable
oxygen.
bond.
I can take that pair and move it up here. It doesn't matter whether you move that pair or that pair or that pair, it's all the same unit. Okay? So when I do that, what I end up with is that. So hydrogen has 2, hydrogen has 2, oxygen has 8, carbon has 8, hydrogen made its 1 bond that it likes to make, oxygen made 2 bonds, which it likes to make, and carbon made 1, 2, 3, 4 bonds. So everything is happy there. So we finished that structure. That is just the structure. You don't need to draw the circles. I just drawn through those so you can see where the electrons are going. So in your slides, there are step-by-step instructions on how we did that. Next one we're going to do is hydrogen cyanide. How many total electrons do we have? We have 1 plus 4 is 5, plus 5 is 10. So we have 10. In this case, this is written in the same format that our skeleton is going to be. Okay? You can always ask me, what the form of the skeleton is, okay? After you do a number of them, you'll see the pattern. But on a quiz, on the final exam, if you're not sure what the skeleton is supposed to be, ask me, okay? So we have H, C, N. We have 10 electrons. What's the first step?
Make a single bond form.
Make a single bond. Something has to be holding them together. So I've now used 4, I have 6 left. Now where do the rest of the 6 go? Just in general.
The outside?
The outside, they go on the outside. So the outside here is the hydrogen and the nitrogen. Does hydrogen need any more?
No.
No. So I'm going to put 6 more, the 6 we haven't used, on nitrogen. Nitrogen now has 8. Are we done? No. What do we have to do?
Just so,
You have to give some to carbon. So I'll only take these and put them here. So now we have. Are we done?
No.
No. What do we need to do?
these
And
8
one more
together.
pair there.
We need to move another pair down. Now are we done? Yes. Hydrogen has 2, carbon has 8, nitrogen has 8. Hydrogen made 1 bond, carbon made 4 bonds, nitrogen made 3 bonds. We're done. Yes.
I'm sorry, I know you just said this, but for when we're forming the skeleton, is there any particular way we need to form it?
As long as you have the right atom in the center. And so I could have put C, H, M, something like that. Okay.
How does this hydrogen goes in the center?
The more you do, you'll start to see a pattern. For the most part, the element that's the furthest left ends up in the center. Okay? Hydrogen will never be in the center. Oxygen will never be in the center. Halogens will never be in the center. Okay? It's usually going to be carbon, nitrogen, phosphorus, or sulfur, most likely.
Okay.
Again, we have those. Now we're going to do some more. We've got CO2. How many total electrons do we have in CO2? 16. So carbon brings 4. Each oxygen brings 6. So we have 12 plus 4, 16. How do you think the skeleton is going to look for CO2?
C in the middle?
C in the middle, and we're going to put O's like that. In general, elements want to be opposite each other. But if you put O and O here, I'm not going to mark it. So, what's the next step?
2 in the middle.
A single bonds. And now, how many do I have left? 14. Are either oxygen happy? So I'm just going to start putting the electrons and see what happens until I run out. We've got 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Are we done? No. What can I do?
Just move 2 from each side.
I move 2 from there and 2 from there. Now I get oxygen, carbon, oxygen. Why would I not? Why would I not do that? Make a triple and a single. It's uneven, but we're going to have structures that are uneven. What rule does this break? No, it doesn't break the octet. We have 8 and 8 and 8. How many bonds has carbon made? 4. How many does it want to make? 4. How many has oxygen made? There it's made 3. There it's made 1. How many does it like to make? 2. So here, each oxygen is made 2. So it's the right one. Now I've got SO2. Now how many electrons do I have? Now I've got 18. What's my structure going to look like?
S.
S in the middle, oxygen's out here. I'm going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Still got 2 more. Where are they going to go?
2 oxygen.
This is the first time we've run into this. Let me go back to that. So we've completed the octet of the outer atoms. Now it says go to now add them to the central atom. So now we're going to add, we have 2 more left. I'm going to stick them on the sulfur here. Are we done?
No.
No. What is wrong here?
It's just not right.
Which rule is not satisfied? Octet. Sulfur only has 6. What can we do to make that sulfur happy?
Give it a double bond with the oxygens.
If I do that,
Not both of them, just one.
not both, exactly. In this case, you can't satisfy all the rules. Because if I move them both, then sulfur is going to have double bonds, single, and a lone pair, just a pair of electrons here. It's going to have 10 electrons. The octet rule is the trump rule. That's the one you have to satisfy, okay? Do what you have to do to match the octet rule, and if the number of bonds rule gets broken and you can't fix it whatsoever, you do the best that you can, and that's the structure. So I'm going to make a double bond here. So here it's asymmetrical. And this oxygen isn't all that happy because I've only made 1 bond. But if I give it a double bond, then sulfur has 10 electrons. And it's more important for everything to have the right number of electrons than to have the right number of bonds. Okay? NO2 minus. Notice the minus charge. How many electrons do we have? How many does nitrogen bring? 5. How many does oxygen bring? 6. So that's 12 total, plus 5 is 17. What do I do with the negative?
You add 1.
I add 1. So again, I have 18. And again, I'm going to have nitrogen, oxygen, oxygen. I'll go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Now what do you think I do? It's pretty clear that we're not going to be able to make everybody happy. But what can we do to get everything in octet? We're going to do the same exact thing. Nitrogen has 8, oxygen has 8, oxygen has 8. And there's one last thing we have to do here. Because it has a negative charge, we have to show that here some way. And the way we do that is we put the whole thing in brackets, put a negative charge. So that's saying that there's one extra electron in this structure.
Ask her a question.
Yeah.
When you move the electrons to nitrogen, does it matter, like, the oxygen that it was taken from, that the two electrons are on top and then there's two in the bottom? No?
Don't worry about it.
All right.
Now we have CHM1030. How many electrons do we have now?
24.
So we've got 6 times 3 is 18,
25.
plus 5,
Plus
plus 1. How many? 18 plus 5 is 23. Plus 1 is 24. We've got 24. What do you think the structure is going to look like here?
The N in the middle,
N in the middle,
and the H, O, with 3 O's.
H, O, O, O. Does anything look wrong there? The N should be in the middle. But how many electrons does nitrogen want? How many does it want in the end? 8. How many bonds does it like to form?
5, right?
Nitrogen. How many bonds does it want to form?
3.
3. It wants to form 3. How many has it formed here?
4.
4. So we're already started clearly wrong. Okay? And so this situation where you will not get something this hard on a quiz or a final exam, but if you draw a structure like that and you immediately know it's not right, ask me. Okay? Because this is not right. In this case, this hydrogen is actually on one of the oxygens down here. Okay? But this is harder than what you will have on a quiz or a final exam. But if you can do this, you can do anything on the quiz or the final exam. Okay? So I have 24. What's my first step? Single bonds. When I add that, I've already made that hydrogen happy, right? There's nothing more I can do about it. I can forget it. So now I just have nitrogen and 3 oxygens to worry about. That hydrogen is done. So I've used 8. I'm going to start putting them on the oxygens until I run out. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. Is everything happy?
No.
What's not happy?
Nitrogen.
Why is nitrogen not happy?
It's only 6.
Down to electrons.
It's only got
6.
6, right? So, what can we do? Again, it's probably pretty clear that whatever we do is not going to end up perfect. But we have to get that nitrogen 8 electrons. What can we do?
Move 2 from the oxygen.
We can move 2 from an oxygen. Which oxygen?
The one from the back.
That one? Would that one work?
Yes.
Would that one work?
No.
Why not?
Because then you're going to take away from hydrogen, which needs to.
We can take that one or that one. But then if we do that,
Then
this
we'll have
one
8.
would have 2 plus 1 is 3 bonds.
Yeah.
The oxygens want to have 2. So I can take that one or I can take these. In the end, I'm going to get that. Okay? what you are going to do on the quiz and the final exam, the types of structures that you have to do are going to have one central atom and then things around them. You are not going to have bonds connected to bonds like that. Okay?
One question.
Yes.
You said that the central atom is usually on the left.
Right. But it can't be hydrogen. And so, of the three we have hydrogen, carbon, hydrogen, nitrogen, and oxygen. The leftmost one that is not hydrogen is nitrogen. Pretty much every single time you're going to have a carbon, nitrogen, silicon, phosphorus, or sulfur. I think there'll probably be very few exceptions to that. Okay. So, now we have structures of carbon and hydrogen together. What's special about the carbon-hydrogen bond? We briefly talked about it at the very beginning. Is it ionic?
No.
Is it covalent? Yes. What type of covalent?
Polar.
No.
It's non-polar. Carbon-hydrogen is that exception. Carbon-hydrogen together is non-polar. So, this is carbon, hydrogen. There are 2 carbons, 6 hydrogens. How do you think this structure is going to look? We've got 2 carbons, 6 hydrogens. We've got, we'll put 1 carbon here. Now we'll put another carbon here. And then I can do hydrogen, hydrogen, like that. And if you see something like this, the carbons are going to be bonded to each other, and the hydrogens are going to fill the outside. So how many total electrons do I have?
Eight?
14.
14.
I've got, each carbon brings 4, so there's 8 plus 6, 14. So I'm going to put my single bonds in. I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Is everybody happy?
Wow.
Actually, yeah.
Actually, yeah. Each carbon has 8, each hydrogen has 2, carbons have 4 bonds, hydrogen has 1 bond. We're done. Okay? Now we're going to move down to here. We just lost 2 hydrogens. So I am going to erase that one and that one. And I'm going to erase the electrons that go with it. How many electrons do I have now? Well, not what's drawn, but in the structure. I have 12. So I have 10 drawn. I only have 2 more that I can put in. Where can I put them?
In the middle.
Right there. Carbon has 8, carbon has 8, hydrogens have 2. Now we're going to lose 2 more hydrogens and electrons to go with it. We have C2H2. How many electrons do I have?
10.
10. I have 8 drawn. I only got 2 more. Put a triple bond. Now we're done. Yeah. Be comfortable with these 3. They're not hard, right? But hint, hint, be comfortable with these 3. H2CO. How many electrons? 12. 2 plus 4 is 6, plus 6 is 12. What do you think my structure looks like?
C in the middle, carbon.
C in the middle,
Hydrogen's on top.
hydrogen, hydrogen. No,
Oxygen.
let's take the oxygen. So I've got 12, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Am I done? What do I do?
Oxygen to carbon, zero.
Nose over there. Now I'm done. Looks done to me. Hopefully you're seeing there are patterns here, where it's not that hard once you really get into it. And to me, it is like a puzzle. Where can I put those dots to make everything happen? NF3. How many electrons do I have? Does anybody want to come up and do NF3? Good for you. Somebody help him. How many electrons does he have?
19? No, 26.
26. So what's going to be in the center for it? Got nitrogen in the center.
Two.
You've got 24 over there. You got 2 more. What can he do with his other 2?
The bottom of nitrogen.
Right there. Is he done? Yeah. Everything's got 8. Nitrogen has 3 bonds. Fluorines have 1 bond. You picked an easy one. Smart man. H2O. Somebody want to do water. How hard can water be, right? So, come on. So, I think I've said at least once before, actually water is the most complicated molecule we're going to deal with.
Yay.
I don't think in this case it's going to be all that bad. So I said you're never going to have hydrogen or oxygen in the middle. But all she has is hydrogen and oxygen. And so which one do you think is going to be in the middle? Something's got to be in the middle.
Oxygen.
Put oxygen in the middle. Hydrogen can't be because it can only form 1 bond. So it can't bond to 2 different oxygens. So she'll put her oxygen in the middle. Got her 2 hydrogens. How many electrons does she have?
8.
She's got 8. Is she done? She's done. Thank you. I think I know what's. So that is Lewis structures. Okay. You're gonna be tested on that, and that's also going to be the starting point for the next thing we're going to talk about. Okay, we're going to get some beast problems coming up. Okay, where you're going to have to go through a lot of steps to get to the final answer, okay? What we're going to do is we're going to take this, and we're going to figure out the shape of a molecule, okay? Because we're drawing these on a two-dimensional whiteboard. The molecules exist in three-dimensional space. So we have to figure out, how do we take this and translate it into real life? And all molecules have shapes, okay? And those shapes affect the way they interact with things. And maybe the most obvious to you is the shape determines the taste and the smell of the molecule. So if you have two molecules that have pretty much the same shape, they're going to have the same taste and smell. So on your tongue, your taste buds, they're basically like a lock. And if you have a molecule that comes around, that's the key that fits in that lock, your brain is going to sense that as a certain taste. So, a perfect example of this is the taste buds that sense sweetness. They're designed to sense sugars. You've heard of Splenda, right? Does anybody know the difference between Splenda and sugar? You remember what they're, go ahead.
I was going to say that the number one thing I noticed between Splenda and sugar is when you put it into coffee or any type of drink, basically it gets sweeter a lot, it really overpowers your drink, but with sugar it kind of dissolves from it.
Splenda is actually sweeter than sugar. I mean, if you go and you're sitting at a table at a restaurant and you look at the packets of the sugar and the NutraSweet and the Splenda and the Sweet and Low, they all have different amounts, right? And the sugar is by far the biggest one, the heaviest packet. So it is sweeter. But on the molecular scale, anybody know what's different? Probably not. You remember what the tagline, the thing they say at the end of the Splenda commercials? They say it's made from sugar, so it tastes like sugar. Okay? Sugar molecules look like this. These reds and the whites attached to the blacks are carbons. The reds and the whites are oxygens and hydrogens. They're OHs, they're hydroxyl or hydroxide groups. Okay? What Splenda does is they actually start with sugar and they replace a lot of these OHs with chlorines. And a chlorine atom is about the same size as an OH group. And so it fits your tongue perfectly, even better than the sugar does. And so it tastes sweet. Your tongue can't tell the difference between the sugar and the Splenda. But these OHs are very, very important in metabolism. They're where the energy comes from. And so the Splenda has no OHs, it has chlorines. So Splenda has no calories. So that is where this comes from. And for the smell, when I was an undergraduate, I worked at a chemical company at the same time, okay? And we worked with personal care products. I made sunscreen, I made lotion, all kinds of mascara and things like that. One of the things we worked with were scents, fragrances. And we had a company tell us that they wanted us to make something that had a scent in it called limonene. And I was a college student. I had no idea what limonene was. I didn't know why they wanted it in there. My boss was actually a theoretical physicist that got moved to making sunscreens. Okay? So he had no idea what limonene was. So we went online, we ordered some limonene, it came in, I opened the bottle, and it stunk really, really bad. And I said, something's not right. So I took it to my boss, and I said, does this seem right to you? And he opened the bottle, and he said, well, in British cuss words, no, it doesn't smell right. Well, let me check my email, okay? So he checked his email, and it said limonene. And the bottle said limonene. So we figured, okay, what do we know? this is what they want in there. So I made the formulation with it. We mailed it to them. They called him and said, "What are you doing? This smells horrible." Turns out there are two forms of limonene. Okay, imagine this is limonene. This bond, it's two-dimensional. It's hard to tell. This bond sticks out at you. You can also take that bond and stick it away from you. What we had ordered was this one, and the one that smells good is that one. And the only difference is we didn't know what it meant at the time. There was our limonene and L limonene. So we said, I don't know what the difference is, or the cheaper one. Turns out we needed the more expensive one. So a very, very small differences in shape can make a huge difference here. And that's especially true in biological systems, okay? All of the amino acids in our body are L amino acids. If they are R, they won't work. All of the nucleotides in our DNA and our RNA have specific shapes to them. All of the proteins in our body have specific shapes to them. And if that shape is not right, they will not work. So shape is something we really have to be aware of when we're dealing with these molecules. And we can predict the shape of molecules. It's not just a matter of making it and figuring what the shape is. We can predict what that shape is going to be. And the very first step of predicting that shape is to write the Lewis structure. Okay? So, like I said, you're going to ask a question, and before you can even start to answer that question, you have to do a whole other question and draw the Lewis structure. Okay? So what a lot of times the way you'll see this on an exam or a quiz is it'll be a multi-part question. Where part A is draw the Lewis structure, and then I grade that. And then part B is, okay, now you've got that, tell me the structure. Okay? So they're separate, but I don't make you do two completely separate things. So we draw the Lewis structure, and then we use what we call VSEPR theory. It's really hard to say that. So everyone calls it Vesper theory. We will call it Vesper theory. We can call it whatever you want. Okay. And what this works on is the fact that we have all these electrons flying around. All of those electrons are negatively charged. And if you have two things that are negatively charged, they're going to repel each other. So when we have this three-dimensional structure, everything is going to orient themselves so that the electrons are as far away from each other as possible. Okay? And before we move on, we're going to do a three-dimensional model so that you can see how this works. Supposedly, we have molecular models for this somewhere. I don't know where they are, okay? But fruit seems to work pretty well. So we have an apple. That's going to be our center atom. We have toothpicks for our bonds. And we have Curious George fruit snacks for atoms. Okay? So, first thing we're going to do is we're going to put two atoms on our center atom. And we're going to try to make them as far away from each other as possible. So I've got my apple. And I have to stick these two Curious George, well, that's a Curious George. They're both Curious Georges. You have an orange George and a red George. So where can I stick these two so that they're as far apart from each other as possible?
One at the top, one at the bottom.
I can stick one at the top and stick one at the bottom. It would have done the same thing if I put one on that side, one on that side, one on this side, one on that side. 2 is easy. Just put them opposite each other, right? So now let's add a third one. Now I have 3. What can I do with the third? If I put it there, are those 3 as far away from each other as they possibly can be?
No.
No, they're not. What can I do?
Stack on top of each other?
Move the linear side to different angle.
At angles. If I do that, it's like a peace sign, right? For a Mercedes symbol. It's thirds. Can you see thirds? In a perfect world, they're exact thirds, but I'm not a perfect world. Okay. So they're as far away from each other as possible. So that's 3. Now we're going to add a 4th. We're not going to, this doesn't go past 4. Oh, it's just a George head. What can I do with my 4th?
Put it in the same angle. Oh, wait.
You have
Wait, no, not there. Move that one to the left, and then
Move
put
this
the
one over
yeah,
here?
Yeah.
And where does this one go?
Right
Here?
Yeah.
Is that as far away from each other as they can possibly be?
Looks like
If this was drawn on the board, that's as far away from each other as they can possibly be. But the board is in 2 dimensions. Apple's in 3 dimensions. What can I do? There's something I can do to this to get them further apart from each other. Anybody see it?
You put the 2 the other way.
Anybody see it? No?
I was thinking opposite sides.
You were really close.
I was thinking, now I lost it. I was thinking opposite sides somehow, but.
What we need to do is if I leave that one there, and I take these 3 out, start from scratch, okay? What I'm going to do is I'm going to put these 3 in thirds, but they want to get away from that one. So they're going to be like that. Again, in a perfect world, it would be perfect. But basically, you have a triangle pyramid, and then one sticking out the top. So the distance between these 2 is the same as the distance between these 2, and these 2, and those 2, and any combination you can possibly do. In a perfect world, it would be like that, okay? We will do a lab with actual modeling kits in lab, but they're so small they don't work in a class like this. When we do that, you'll really see this 3-dimensional shape where they're all parts of it. So, I said each of those gummies represented an atom, okay? When we're trying to get these things as far away from each other as possible, it's not really the atoms that matter. It's the electrons. And so when we figure out what we're going to call parent structure, we're going to count the number of things around our central atom. And when I say things, a thing is an electron pair that's not involved in a bond. It's a single bond, a double bond, or a triple bond. Any of these four things count as one thing. A triple bond counts the same as a pair that does nothing. Okay? So we have four types of things. And over again, I'm going to ask you how many things are on the center atom. So when we do this, we're going to maximize the distance between those things. So this is what we did. This is when they're two, they're opposite each other. 3 is in thirds. 4 is like this. Because they're big fat balloons, it's hard to tell that they're kind of pointing down a little bit. But we have 3 at the bottom pointing down and away from each other in thirds, and a fourth one sticking straight up. Okay? So the simplest molecule to look at this is methane. Methane has a carbon in the middle and 4 hydrogens going around it. How many things are on that center atom? There are 4 things. There are 4 single bonds. That's 4 things. If you have 4 things around a center atom, they're going to make this shape. And when they make that shape, the angle between them is 109.5 degrees. You're going to need to know these angles. This is the first one. This is the oddest one. It's 109.5. It's basically seemingly a random number. Okay? 109.5 if you have 4 things. And we call this shape with 4 things at 109.5 degrees a tetrahedral shape. Tetrahedral. 109.5. If we have 3 things where they're all in line with each other, so we have that. They're all in line with each other. We say they're in the same plane. If you're familiar with that word, plane, P-L-A-N-E, like airplane, but plane. Okay. And so if something is all in the same plane, we call it planar. So this is called trigonal planar. Trigonal because there's 3, like 3. Okay. I went to say 3, like the shape that has 3 sides, and then caught myself. Okay. So this is trigonal planar, and this is 120 degrees. Now this one, the 120 actually makes sense. Why does 120 make sense here?
360.
360. To go all the way around, we need 360. If we divide 360 into thirds, it's 120, 120, 120. Okay? And then if we just have 2 things, we have that. We call that linear. And again, the angle makes sense. Why is it 180? Half of 360 is 180. So it's 180, 180, 180 plus 180 is 360. You're right back where you started. Okay. So these are our 3 parent structures. You need to know those names. You need to know these angles. Okay? It's going to come up over and over and over again. Take a break a little bit. What we're going to get into is meaty. Let's start at 7:30 on that clock. Don't try to do this. This is what we're working on. How many things are on that? There are 3 single bonds and a lone pair. So there are 4 things. So this is assuming there are way on it.
This is my final said, why? It's not right.
It's not right.
Yes, because I remember.
Does anybody want to carry this, George? Yeah. A non-stuck one?
Yeah, sure.
Oh, hello. Oh, just. Does somebody want a stuck, George? Stuck monkey? You want a stuck monkey? I got 2 more. I got 3 more. This one is sitting on the counter. You probably don't. Everybody want these? Want the apple? It's from before Christmas. That's why it's here. I always find old fruit and bring it.
Probably not a good idea.
Huh?
You want to poison us?
I'm sure it's just fine. It's just very ripe. It's not like Sleeping Beauty. I don't need a poison apple to put you to sleep. I have chemistry.
I mean, if I can stick the
I mean, well, technically, didn't she use chemistry to poison her in a way? She did potions.
I guess
Potions.
that's alchemy. We're not alchemists. We're chemists.
What is the study of alchemy exactly?
It's potions. It's basically the study of when they were mixing, used to mix things, and they had no idea what they were doing.
Yeah.
And they thought there was magic involved.
Yeah. There's also a really cool show called Full Metal Alchemist, which is more magic, but it's still pretty cool. Is there any trick memorizing
The ions.
Yeah.
The only tricks I can recommend is like nitrate or nitrate and nitrite. If you remember one of them, I remember the nitrate, and I remember nitrite has one less oxygen. And the same thing with nitric acid and nitrous acid. Sulfuric and sulfurous.
And what's that one?
It's nitric. Well, sulfate makes sulfuric acid. sulfite, like sulfurous.
Nitrogen is 3 and nitrogen
Yes.
is 2.
Yep.
That was all, I was just making sure.
Keep using this, like, different papers for this. Can I just use one for the rest of this work?
Yeah. Yeah. You just have to not lose in lab. Four. Yeah, if you take 14, you drop 4.
But no homework, right?
Only thing that gets dropped is 4 quizzes.
And one paper.
One, but you have to do the makeup for the lab. It was the question was actually asked what happens and so a lot of people you found the math, you didn't tell me that. So this is maybe similar to elements. This is just arsenic. So the isotope includes the AS. So this is the real number problem, which is 33. And then that is the mass number, which is proton plus. It said it has, it tells you right here. The P is the P orbital.
Oh. Okay, thank you.
K here.
Stuff we do around as well.
You don't write the one.
Yeah,
K,
it's
K.
okay.
Which is behind we have to memorize. BO3, 3 minus charge. So you're going to treat it just like you would treat the nitrite of sulfate. It's a package. It's a BO3. Stay BO3. And it has 3 minus charge. So 3 minus charge in the borate is going to go on the nickel. And 2 charge on the nickel is going to go on the borate. Missing anybody? Is there anybody that was here to begin with? Don't. So, I was just reminded about the homework. A couple people have asked me about it. The homework for this week is different, okay? When we did the syllabus, first week, I said that there's going to be some cumulative homework assignments, okay? This is the first one. This is so that when you get to the final exam, the biggest, most important assignment of the entire semester, you didn't forget everything from the first 14 weeks of the semester, okay? You need to keep everything in mind. So this is the homework for this week. There are a bunch, multiple choice, and some written questions.
That's a lot of homework.
I already started on it.
But there are 39 and 40 questions, but there's no other online portion, okay? And you've done these questions before. You've changed the wording a little bit, but you've done them before. So hopefully, 39 questions that you've done before shouldn't take that long, okay? If you look, when you look at the end, there are some questions here that have to do with today's lecture, okay? So these are going to be what you focus on for next week's quiz, okay? We don't have the online portion, so you're looking at these questions on the last page for next week's quiz, okay? And so you can print them out. Actually, it goes on these and those. Okay? So you can print them out. You can circle your answers on here. You're welcome to do that. I would thank you if you just took a piece of paper and wrote 1A, 2B, 3C, something like that. So I don't have to flip page after page after page after page, 4 answers on each page. Okay? But I will accept it either way. Later on, when we get to be bigger, because this is cumulative, this is after 5 weeks, there's going to be one after 10 weeks. That one's going to be huge, okay? That one, I'm not going to let you just circle answers, okay? I'm going to have an answer sheet that you have to put your answers on, okay? This one, do what you got to do, okay? It's due a week from today, just like normal. When they get bigger, you're going to have 2 weeks, okay? But for this one, 42 questions, most of them you've done before, shouldn't take that long, okay?
So this is due next class.
Next class.
All right.
Okay. So, we know our Lewis structures. We know the names of our parent structures. What are the 3 parent structures? Tetra something, that's not going to get you points. Tetrahedral, linear, trigonal planar, right? Those are our 3. But we have to figure out which one it is. We have to figure out how many things are on our center atom. And in order to do that, we have to draw the Lewis structure. don't try it without drawing the Lewis structure. If you just look at that, how many things that look like they're on that nitrogen? It looks like there are 3. We're going to find out there's not 3. Okay? So what do you think's in the middle? Nitrogen, hydrogen, hydrogen. How many electrons do I have? 8. Got 8. 1, 2, 3, 4, 5, 6, 7, 8. Am I done? Yes. How many things are on that nitrogen? 4. 3 single bonds and a lone pair. We call that a lone pair. They all count as a thing. So there are 4 things. So what is the parent structure of this molecule? Tetrahedral. So you drew the Lewis structure in order to figure out the parent structure. Okay? What are the bond angles in this molecule?
109.5.
109.5. That's the one you just got to remember. Unless you can think in your head about 3-dimensional angles and figure out, of course it's 109.5. Okay? I don't think that's going to happen. So you got to remember that. We got CO2. We actually did CO2 before. Do you remember what the electrons look like? Here's that. How many things are on that center atom?
4.
2. Double bonds still only count as one thing. Even if it's a triple bond, it's one thing. So there are 2 things. What is the parent structure? Linear. What are the bond angles?
180.
180. You've got SO2. Do you remember what SO2 looked like? This was the one that was asymmetric, like that. How many things are on that sulfur? 2. Actually, no, this isn't.
3.
Now it's right.
3.
Now there are 3 things. There's a single bond, a double bond, and a lone pair. So there's 3 things. What's the parent structure?
Oh,
No, triangle.
Trigonal,
Planar.
planar. Trigonal, planar. And the last one was the water. Now she drew it like that. Was there a reason you drew it like that? I'm telling you, because it's wrong. But
Well, I thought it looked correct.
okay.
It made I don't know, I just remember kind of doing it. I had a chemistry class in high school, and I remember my teacher drew it like that, so I just kind of...
You might have heard, might, maybe you're not as big a nerd as I am, but you might have heard that water is bent. Anybody heard that?
Isn't it kind of like an L shape?
It's an L shape, it's bent, like that. But why is it like that and not like that? Okay? So we are going to do the structure to figure out why it's like that and not that. So that is our water Lewis structure. How many things are on our center atom?
Like 4.
There are 4, all right? We've got 4 things on our center atom. What is the parent structure? Tetrahedral. But when we talk about the shape of a molecule, the shape of a molecule is actually different than the parent structure of the molecule. Okay? In the shape, we are only dealing with atoms. In the parent structure, we're dealing with things. And lone pairs count as things. In shapes, we only care about atoms. So if we draw our parent structure for water, and it looks like that, we have our tetrahedral shape. When you then go to the shape of it. Sorry, we have the tetrahedral parent structure. Let me correct myself. When we then go to the shape, we basically pretend the lone pair electrons don't exist. If you've drawn it on paper, you can erase them. If you go home and you find a plum or a peach and you stick toothpicks in it, you can just pluck out the toothpicks for the lone pair. So if we take this and we ignore that, what we have is that. Okay? And this is a concept that some people have trouble with. Taking the structure, the parent structure that has everything here, and imagining what it looks like without the lone pairs. Okay? If you struggle with this, make sure that you figure out what you're doing before you get too far.
Is that only for water, or?
We're going to do it for everything. Okay?
Oh, okay.
That list of 3 parent structures is going to grow into a big list of shapes. So again, here's our water, and we're going to ignore that, and we're left with that. And I said water is bent. That looks bent to me. Okay? This is CO2. You have CO2 and SO2. In terms of Lewis structure, they look very, very similar, right? But the shape is different. One is straight, one is bent. Why? Right. Here we have 3 things. So here we only have 2. There's 2, it's linear, it's straight. And there are no lone pairs on the center atom, and so our parent structure is our shape. Because we don't erase anything, it stays the same. Here, we have 3 things. So it's trigonal planar. So in reality, it's really like that. And so then, when you erase the lone pair to go to the shape, you have a bent molecule again. That's why you have to do the Lewis structure. You have to know how many things so that you can draw the parent structure and then erase the lone pairs. So that's what we did. Draw the Lewis structure formula, figure out the parent structure, and then erase the lone pair electrons. So this is our big table of shapes. And you need to know all of them. Okay? So the way this is organized, is on the left here is a generalized formula. So this is saying we have a center atom and then 2 things on it. Okay? And here, this tells us how many of those things are atoms. And then there's another column for how many are lone pairs. If we have only 2 things, by default, they have to be atoms. Because if one of them is a lone pair, then you just have 1 atom bonded to another atom. Then it's just a bond. So, if you have 2 things, the parent structure is linear. If there are no lone pairs, you can't erase anything. So the shape is also linear. So it's linear. Then we come down here. If we have 3 things, we can have a center atom with 3 atoms and 0 lone pairs, or we can have 2 atoms and 1 lone pair. That's still 3 things. If there are 3 things, the parent structure is trigonal planar for both of them. For this and this, the parent structure is trigonal planar. Then you have to erase the lone pairs. If all 3 are atoms, you erase nothing. So your shape is the same as your parent structure, and the shape is trigonal planar. But if one of them is an unshared pair of electrons, like we had here, this is now gone, and it's no longer trigonal planar. There are only two atoms, so it's not trigonal, right? We call that bent. But because it's trigonal planar parent structure, the angles here are still 120. The angles are based on the parent structure, not the shape. Then if we go to tetrahedral, we can have 4 atoms, so our shape is also tetrahedral. If we have one lone pair, we're basically just left with the pyramid part at the bottom. And that's called trigonal pyramidal, not trigonal planar, trigonal pyramidal. And if we have 2 lone pairs, those go away, like in our water, and we have another bend. What are the bond angles in these 3 shapes? 109.5. So, here we have a bent that has 109.5. Here we have a bent that has 120. So we are 2 different forms of bent. Depends on what the parent structure was that led you there. Okay? If you know someone in one of the other sections of this class, there are 2 other professors. One is Dr. Owusu, the other one's another adjunct who I don't know how she teaches this. Okay? Dr. Owusu adds a little detail here that I'm not going to add. Okay? So I'm going to tell you this so that you don't get confused if you talk to your friend in one of her classes. But you are not required to know this. In a tetrahedral shape, if you have lone pairs, it will actually slightly change the bond angle. Okay? Imagine here, this lone pair is going to push these down closer to each other a little bit. So it would not be 109.5. It would be something less than that. That's what she teaches her students. For us, if it's tetrahedral parent structure, it is 109.5. Okay? On the final exam, if that's an answer, you write 109.5. Okay? And then I will tell her that I told you that's the right answer, and she needs to mark that correctly. We've done that in the past, it works, okay? Write 109.5 unless you are so confident in yourself that you can write the technically correct answer, okay? I would not worry about that. Correct is good enough in here. You don't have to be technically correct, okay? So, we're going to figure out the shape of the nitrite ion. And we have to figure out what the bond angle is. So the nitrite, NOO, we had 18. 1, 2, 16, 17, 18. That comes over here. So that's our Lewis structure. I whizzed through it because we had done that one before. How many things are on my center atom?
2.
3. A single bond, a double bond, and a lone pair. There are 3 things. What is my parent structure? Trigonal planar. Trigonal planar is my parent structure. How many of those things are lone pairs? 1. So on that table, what is the name of the shape if you start with trigonal planar and you erase one? It's bent, okay? You can try to imagine it in your head. Trigonal planar was the one that you had the thirds. So if you erase one of them, you have bent, okay? So it's bent. The name of the shape is bent. what are the bond angles in that ion? Why is it 120?
Triangle.
Because it came from trigonal planar. Remember, there are two types of bend. This is the bend that came from trigonal planar. So it's 120. The last thing you have to do with these shapes is deal with polarity. Okay? The type of question that you're going to see. Part A, draw the Lewis structure. Part B, draw the shape, indicate the bond angles, and indicate the polarity. Okay? Polarity of a molecule is not difficult, but it's something that tricks a lot of people up. Okay? So, conceptually, this does not make sense to you. Don't just push forward. Okay? Stop and make sure that it makes sense to you. If you have a molecule that's made up of only two atoms, so it's diatomic. So your whole molecule is two atoms connected by a bond. Whatever the polarity of that bond is the polarity of your molecule. So, if you have a polar covalent bond, you're going to have a polar molecule. If you have a non-polar covalent bond, you're going to have a non-polar molecule. Because that whole molecule is consisting of one bond. So whatever that bond is the molecule. Where it gets trickier is when we have more than two. A non-polar molecule either has all non-polar bonds, so either it's all made up of the same element, or we have carbon and hydrogen. That one is easy. What's trickier is when we have polar bonds that cancel out. If they cancel out, it's because they have the same polarity and they are directly opposite of each other. Okay? So imagine I'm standing here and I hold my arms out and one person pulls me that way, one person pulls me that way. Both of them are pulling me. That's a polar bond and a polar bond. But if they pull with the same strength, I'm not going to move. They completely and perfectly cancel each other out. So overall, I stay right where I am. That is a non-polar molecule. If you have a polar molecule, you have polar bonds, and they do not cancel each other out. So the easy part is figuring out whether you have polar or non-polar bonds. The tricky part is figuring out whether they cancel each other out. Okay? So this is water. Okay? We said water was bent. This is water. Because we have polar bonds, we get these partial positives and partial negatives. Partial positive, partial negatives were in the video, correct?
Yes.
Okay. So remember, this is the lowercase delta. That's saying it's a delta negative, delta positive. That means it's halfway to a negative and halfway to a positive. It's a covalent bond, so it's not an actual positive and negative. But because it's a polar covalent, we're halfway there. So here, you have this molecule. What you have to do is you have to look at it, and you say, is it symmetrical? Can I draw a line through it where there's more positives on one side than on the other? Or is there more negatives on it than on the other? Looking at that water molecule, is there a way that I can draw a line through the center of it and so that it's not a mirror image of each other? Yes. If I draw a line, a vertical line right through here, I have two hydrogens on the right, 0 on the left. I have two partial positives on the right, I have a partial negative on the left. That is not a mirror image of each other. These polar bonds do not cancel out. So this molecule is a polar molecule. If we come over here, this is carbon dioxide. We have a partial positive in the middle and two partial negatives. Is there a way that you can draw a line through the middle of that molecule and not have a mirror image? If I draw the line like this, is it a mirror image? Yes. I have half a black one and a red one on each side. If I draw it like this, is it a mirror image? Yes. So, that one is non-polar. We have two polar bonds between carbon and oxygen, but they're directly opposite of each other. They're opposite each other and they're equal to each other because they're both carbon-oxygen. So they cancel. This is non-polar. What this picture is showing is if you put a polar molecule in an electrical field, it's going to move. If you put a non-polar molecule in an electrical field, it won't move. Yes?
Is that going to be the same for all linear?
Not necessarily. If what's on both sides is the same, it would be. But I'm not guaranteeing this is something that would actually exist. But if you have a linear molecule that looks like that, it's linear. But that bond is going to pull, this bond is going to pull harder than that one.
So only if it's the same on the outside.
Right. They have to be the same bond, opposite of each other. So this is trigonal planar. In this case, we have 3 sulfur-oxygen bonds. They are not directly opposite of each other, but they're equally spaced out. They're in thirds. So as a whole, those 3 cancel each other out. Okay? If I draw a line like that, it's a mirror image, right? It's tempting to say, if I draw a line like that, it's not a mirror image. But it kind of is, if you really think about it. This oxygen is further away from that sulfur in terms of up and down than these are. So these two are half as far away. So half plus a half is equal to 1. Okay? So it's like I'm standing here and I have 3 arms, and people are pulling me in 3 directions in thirds. I'm going to stay in place. Okay? This is where it starts to get tricky to see whether it is polar or non-polar. If you had these 3, they're all the same bond and they're equally spread apart, it's going to be non-polar. But if we had oxygen, and then another sulfur, it's all bets are out the window. Okay? Then it is not going to be non-polar. Then it's definitely polar. This is a tetrahedron. We have a carbon and 4 chlorines. Again, these 4 chlorines actually cancel each other out. So if you have that molecule, would you call that polar or non-polar?
No,
Polar. Why is it polar?
You put a line here, it's the same? Is that where you're supposed to?
The line, if it's the same, it means it's non-polar.
Oh.
If I draw a line like this, though, I have 3 chlorines on the bottom and hydrogen on the top. That is definitely not a mirror image of each other. So that's polar. What about that?
also polar.
It's also polar. I draw a line like here, I have a chlorine on one side and hydrogens everywhere else. And again here, if I draw a line like that, in 3 dimensions, I have 2 chlorines sticking out, 2 hydrogens sticking back.
So when it's not.
If it's not the same, if it's not symmetrical, it's polar. Polar, non-polar? Polar. If I draw a line like that, the red ones are on one side. Polar, non-polar? Polar. Got green ones on the bottom, white ones on the top. Before you answer this one, let me point out, these green ones are pointing down a little bit. Polar or non-polar? Polar. The green ones are pointing down. There's none pointing up. So that is polar. In this one, it's planar. They're all in one line. Polar or non-polar?
Non-polar.
Non-polar. That's like that. So that's non-polar. They all are in thirds, they cancel each other out. We'll do two of these and then the quiz is going to be another short one. So we've got NH3. It seems like an easy question. Is it polar or non-polar? Can you look at NH3 and tell me if it's polar or non-polar? No. You have to draw a Lewis structure, you have to find the parent structure, you have to find the shape. Then you have to figure out whether it's polar or non-polar. We've got NH3 ends up looking like that. That's the parent structure. Tetrahedral. So basically we end up with that. What is the shape?
Try. It's a, well,
So we have one lone pair, so I'm going to erase that. And what's that called?
a trigonal.
Trigonal what? Pyramidal. Trigonal pyramidal. So the shape is trigonal pyramidal. We have, this is an N, and we have H, H, H. Is that polar or non-polar?
That's cool.
That's polar. We have H's on the bottom, nothing on top. CS2. We're going to do this one. CSS 12 plus 4 is 16. 16, so it looks like CO2. What's my parent structure for that? How many things are on that carbon?
Four.
There are two things. There are two double bonds that it's hard to tell. But there are two double bonds, so there are two things with linear. So what is the shape? Linear. Is it polar or non-polar? Polar. Non-polar. Even though this bond is polar and that bond is polar, they're directly opposite each other. So they cancel each other out. So it's non-polar. We're going to skip these last ones. You can do those for homework. If you have questions about this, there are a lot of steps here. Ask me. Okay? Obviously, if you mess up the Lewis structure, you're going to get everything after it wrong unless you're really lucky. The last thing is like dissolved light. Have you ever heard the term like dissolved light? Yes. Basically that means if you want to dissolve something in another one, they need to be similar to each other. Water and oil don't mix. Water is polar. Oil is non-polar. And so they don't mix. Salt is polar. Salt polar, salt dissolved in water. Yes. Water's polar, salt's polar. So they dissolve in each other. If you want to dissolve something that's non-polar, if you want to dissolve oil, what do you need?
Some oil-based.
Something oil-based, right? In order to dissolve something non-polar, you need something else that's non-polar. So non-polar covalent bonds non-polar covalent compounds dissolve in non-polar liquids. We're not going to, at one point this is one of those self-concepts. But you're working in a lab and you're told to make up a cholesterol solution to give a patient. They don't tell you what to make it up, what you're supposed to dissolve your cholesterol in. Okay? That is cholesterol. Okay? You have water, you have ethanol, you have octanol. This is ethanol, this is octanol. Okay? When you're looking at a big molecule like this, what you're looking for are the number of atoms that are not carbon or hydrogen. Okay? The more non-carbon or hydrogens that you have, the more polar your molecule is. Here we have an OH, an OH. So we have one oxygen, one oxygen. This one is actually more non-polar because there are more of this whole thing, which is non-polar, as compared to this. So, if you have to dissolve that monster of a cholesterol molecule, you're going to use water, ethanol, or octanol. What do you think? Does that look polar or non-polar? Are there a lot of things that are not carbon or oxygen? No. So this is very, very non-polar. So you want your solvent to be the most non-polar thing you can get your hands on.
Octanol.
Which would be, water is very, very polar. This is more polar than that because there are fewer of the carbons here. This is your least polar thing. So you're going to dissolve your cholesterol in octanol. Okay. Okay. Questions? Questions? Now back to the naming. Okay. Now that we've done the naming,